So last time we calculated the Fock term of the Hatree-Fock energy, which is the Coulomb potential energy by Hatree-Fock approximation, meaning we consider this H0, which is a non-interacting somnifer gas, as the unperturbed eigenstate of this Coulomb interacting electron gas, and then we perturbed around this unperturbed eigenstate by treating this Coulomb term a small perturbation, and we do perturbation and we find this the first non-trivial term that give us is this integral over this overlapping volume between these two Fermi sphere at zero temperature. And this is your homework, that you could verify that this volume, which is a shaded region, is given by this number. And we add this, and note that there's a minus sign in front of this, the Fock exchange energy. The minus sign comes from this Pauli principle for two electrons. And the first term is the kinetic energy of a free electron, which is that value. The next thing we need to do is to calculate the predictions for various experimental observables that could be compared with this Hatree-Fock theory. And you'll find that this Hatree-Fock predictions are all wrong, incompatible with all the existing experiments, but we know why. Okay? But before we move on to the correct approach to the Coulomb interaction in metals, we first need to compare the predictions from Hatree-Fock theory with the experimental observations. So the first thing that we can compare is the elementary excitation energy, which is this electron hole pair excitations for nearly free electron gas. And this is a Fermi sphere, and you could imagine that you have this particle hole pair excitations. And remember now that this total energy of this system is given by this Hatree-Fock. Within such a framework, we need to calculate the energy cost to create such an electron hole pair. So you could separate this calculation into two parts. The first part is to remove an electron within the Fermi surface with a momentum p, and then I place this electron in another excited state above the Fermi surface with momentum p prime. And the total energy cost is given by the subtraction of these two energies, because when you remove electrons, suppose you it costs you energy, but then you put these electrons to the excited state, then you gain energy. Okay, so the total energy required to take one electron out of the Fermi surface and put it in the excited state is actually the difference between these two energies. One is to cost you energy, another is that you gain energy. So it's the opposite motion. So if I call this W, P prime is the energy required to remove one electron out of the Fermi surface, and this WP is the energy required to remove one electron. Then this energy is given by this Hatree-Fock energy, the derivative of the Hatree-Fock energy with respect to this occupation. Remember, the Hamiltonian in the Hatree-Fock theory is given by the average kinetic energy per particle multiplied by the occupation number, right? And sum over k prime, and you know that this volume, so this is n 2 pi e squared over q squared. Okay? And this is what given by an f of k and f of k prime, right? So in other words, the second term, the Fock term exchange energy, is given by the product of the two Fermi functions. One is centered at k, another is k prime, and this is total energy of Hatree-Fock theory. But here we don't want that. We want the energy required to actually remove just one electron, not all electron, but just one electron. Therefore, we need to take the derivative of this total energy with respect to the number of particles, and that quantity is the average energy per particle. But this particular particle is at momentum p, state p, so which means that you need to take the ratio of these two, or derivative of this Hatree-Fock energy with respect to the occupation number, but this occupation number is at not arbitrary, but a particular momentum p. And that is the energy per electron when this electron is at state p, and that is the energy cost to remove one electron at state p. And if you take the derivative of Hatree-Fock energy with respect to mp, what you get is you simply just plug in this Hatree-Fock Hamiltonian and take the thermal average of these two terms, and then take the derivative of this term with respect to the occupation number, the average occupation number at state p. So you immediately cancel this occupation because this is simply just a derivative. And you could just take approximation that this is something that decouple. So then when you take the derivative of this term, you get rid of one of the occupation, which is that k equals to p, and so on. And similarly, you could calculate Wp prime, where you put one electron back to this excited state, and with momentum p prime, and that energy is given by this Wp prime. So you want to take the difference between these two energies to estimate the total, the net energy cost to create such an electron hole pair. And then this delta W is given by these two energy difference. But if p and p prime are very close to each other, they are very close to the Fermi surface, and this p and p prime are just very, very small in difference. So we can Taylor expand this difference, which is delta p dotted gradient p and this stuff. So by Taylor expansion, this is simply just the derivative of this W with respect to p and multiplied by delta p, which is simply p prime minus p. Of course, this is a vector and so on. So then we need to calculate this partial W partial p. So what is the partial W partial p? Which is what? Delta W divided by delta p, which is this thing. Suppose that this dot product is just simply the product of these two magnitudes. Suppose that this is going along the same direction, p and p prime. If you just move this delta p to the left side of the equation, and you get the ratio between delta p and delta W and delta p, and which is given by the right hand side, which is the this partial p of this stuff. And the stuff inside the bracket is the derivative of Hatree-Fock energy with respect to the occupation. So you know what it is. So this is given by partial epsilon p, partial p minus ddp, sum over k, p minus k square, and p. All right, the first term is just the kinetic energy term. When we take the partial derivative of kinetic energy per electron with respect to the momentum, the second term is the Fock exchange energy. You take the derivative of exchange energy with respect to this momentum p, but of course this is not exactly this exchange energy, because you get rid of one of this mp or mp prime. Right? So here this is nk prime, but you should take one derivative of this energy with respect to the mp. So when k equals to p, you simply just get rid of one of the occupation. And this momentum p and p prime are simply dummy variables, so you could just rename this. So therefore, the total elementary excitation energy is this delta W, which is the W dp evaluated at Fermi energy times delta p. So delta W is the derivative of this term times delta p, which is the momentum difference, which is very, very small. So now let's just evaluate this partial W partial p. Evaluate it at Fermi energy and see how large it is. Okay, so from our knowledge or the Fermi liquid theory, we know that both quantities are very, very small, or at least this derivative thing should be finite, and delta P is really, really small because both P and P prime are very close to the Fermi energy. So you multiply two things. One is the finite derivative, another is infinitesimal momentum difference, and we expect that the energy cost to create such an electron hole pair is really very, very small, close to zero, as temperature goes down to zero. That's our expectation, but in reality, you will see that within the Hatree-Fock, you get infinity instead of zero. And let's take a short break. When we come back, just finish this partial W, partial P, and show you that this is indeed a singular divergent quantity within the Hatree-Fock. So you can find this equation and calculations in David Pine's lecture notes, and also probably Kittel's second book. So we expect that this is very easy to have electron hole pair excitations in normal metals because of, as I mentioned, the finite value of this partial W, partial P times almost infinitesimal momentum difference between P and P prime. And both P and P prime are very close to the Fermi momentum. Remember that. But let's see how it looks like when we calculate this quantity within the Hatree-Fock times delta P. Although this delta P is still very, very small, close to zero, but this partial W, partial P diverges. Okay, the reason is this exchange energy within the Hatree-Fock, if you take a derivative of this term with respect to the occupation, and you take another derivative of this term with respect to P, you get something divergence. And the reason is that, as I mentioned, both P and P prime are very close to Fermi surface, right? So, and there's a sum over K where K runs from 0 to all the occupied electron momentum. Okay, so K runs from 0 to Kf, but P is something that's very close to Kf. So we can simply just rewrite this, the first term, approximately at the Fermi energy, K minus Kf square and P. So you immediately notice that in the denominator you get a square, Q square, or square of the momentum transfer, right? And this momentum transfer is written in this form of K minus P, where P is very close to the Fermi momentum, Kf. So you sum over all possible K, right? For all the K's that are far away from the momentum, Fermi momentum, Kf, it is all right. It is finite. But when K is very close to Kf, this term is actually diverges as K close to Kf. Okay, why? Because this is a derivative of this P here, but you could simply just consider this is a P, but you first evaluate this derivative, which is K minus P cubic term, right? When you take the derivative of this term with respect to P, you get 1 over K minus P to the power of 3, right, from your calculus. I don't care about the prefactor or plus minus term. That's a minor thing, but only care about the power in the denominator. So the power in the denominator is actually 3, the cubic term. Okay, but you need to evaluate this thing when P is very close to Kf. So this is approximately given by K minus Kf cubic term, right? But you need to sum over all possible K. So this is 1 over x divergence when x goes to 0, right? So this is like 1 over x cubic term when x goes to 0. So this is a 1 over x cubic divergence when x is very close to 0. And that's how you get a very singular divergent term in 1 over x cubic, okay? And multiply by something that is order of x. And this is 1 over x cubic. So the first term gives you 1 over x cubic divergence. The second term is only linearly in x as s goes to 0. So you multiply this 2 factor, you get still 1 over x squared. So this is approximately 1 over x squared divergence when x goes to 0, which is infinity. All right? And such momentum k that is very close to kf is actually very, very large number of electrons. Remember, there are so many electrons that are very close to the Fermi surface when P is very close to kf. So all these things show within the Fermi surface can be approximately given by this form that all this momentum P very close to Fermi momentum is very close to kf. So all the states that very close Fermi energy will contribute to the 1 over x cubic divergence as x goes to 0. As a result, this whole thing, delta W, Hatree-Fock, gives you 1 over x squared divergence as x goes to 0, and therefore delta W diverges. As a result, all right, okay, which is, of course, not right, physically incorrect, because we know that it is very easy to create such electron-hole pair excitations near the Fermi surface of ordinary metals. How can the Hatree-Fock predictions give us the almost opposite results, that it takes you almost infinite amount of energy to create such electron-hole pair, and which is, of course, totally opposite to what we expect, which is almost costless to create such an electron-hole pair excitation. So what is the problem? What is the problem here? Which means that what is the origin of this divergence? Okay, so if you think about this more carefully, you will see that the origin, the very reason that this term, the exchange energy term, diverges because there is a 1 over q squared dependence of a Coulomb potential. And this 1 over q squared Coulomb potential within the Hatree-Fock is actually a long-range Coulomb force. So I emphasized this many, many times in the past that the Hatree-Fock mistakenly treat the Coulomb potential perturbatively. It is not perturbatively treated because this 1 over q squared, the long-range nature of a unscreened Coulomb potential. So we need to first screen the Coulomb potential and then find the more appropriate language and of the Hamiltonian, such that we could have some small fluctuations instead of just the Coulomb potential as a small perturbation. So we will find that this small perturbation that gives us a reasonable result is not the Coulomb potential itself, but the fluctuations of the density. So the more physical weak perturbations is the electron density fluctuations, rho. So we will define that later. Okay, so but first we need to compare this Hatree-Fock prediction to realistic, experimental observables. And the first thing that we do is to calculate this electron-hole pair excitation energy, and we find that this is divergent with the Hatree-Fock, which is not right. But the reason that the Hatree-Fock fails is because they treat this Coulomb force a long-range interactions, and because of the long-range nature of the Coulomb interactions, this is really strong, not a weak perturbation. But in real solid, this Coulomb potential is actually screened, which is proportional to 1 over r times this decay factor, and this decay factor actually cuts off this long-range tail of a Coulomb potential and make it short-ranged. So the way that we get this Coulomb screening, we'll see later that precisely within this another weak perturbation that we treat this electron density fluctuations as a small perturbation. So instead of Coulomb potential, which is long-range and is treated as a small perturbation, we forget about this approach, and we should consider a small density fluctuations in the realistic solid state materials. Namely, remember, so electron density in the solids actually periodic, because we have a periodic array of ions, right? And you can imagine that electrons that surround the ion cores may also fluctuate in its densities because of this periodic potential of ion core. And we also can imagine that there are some electron hole pair excitations in realistic solid state materials that give rise to some density oscillations or density fluctuations of the electron cloud. So you could imagine that, as a function of the real space coordinates, that the electron density profile may fluctuate slightly, because overall it is a uniform charge background, but locally you may have such periodic modulations of the charge density because of the periodicity of this ion on the lattice, and also because of small density fluctuations of electrons due to the electron hole pair excitations. So you can imagine this in the realistic same metals, there's some small density of electrons that fluctuate back and forth in real space, and we'll see later that this density fluctuations of electrons also occur in time domain, meaning they oscillate like a harmonic oscillator in time, so that there will be some density fluctuations in space and in time. And that small density variations could be captured if you really reformulate the Hamiltonian in terms of the density operators. And this is what we are going to do. If we reformulate this Hamiltonian of electron, Coulomb interacting electron gas, not in terms of the Hatree-Fock language, but in terms of electron density operators, which is in real space is the electron occupation number operator, which defines electron density operator. So remember, this is the occupation for electrons in real space. Okay? And we should rewrite this Hamiltonian in terms of the rho, and both in real space and in momentum space. And that's the correct path to actually to cure this problem. So under such a correct language, we find that delta W indeed vanishes as T goes to 0 and P and P prime goes to KF. So let's just look at another quantity which is related to the electron hole pair excitations called electron quasi-particle energy. So remember, the Hatree-Fock energy per electron is given by the single particle kinetic energy for an electron at state K, and subtracted by the exchange energy, the Fock term. So the quasi-particle energy is the total energy per particle per electron within the Hatree-Fock. So that you take the derivative of the Hatree-Fock energy with respect to the occupation for one electron, meaning so you consider only the energy cost to actually take one electron out. So that's the quasi-particle energy, because that is the energy of a single electron in the presence of the Coulomb potential, so that you get an estimation of this so-called epsilon Ks, or quasi-particle excitation energy. So meaning in the presence of a Coulomb potential, you can imagine that the quadratic behavior of the free electron kinetic energy as a function of momentum actually changes. So this changes to what? So something else. In addition to this quadratic in K behavior, there's additional term due to this exchange energy. So now let's look at the new dispersion relations of a single electron in the presence of the long-range Coulomb potential. So let us just continue calculating this. Remember, this is nothing but this 1 over q squared, and you integrate over dk prime. So you could look at the Kittel's or Ashkov mermions and to see this results of this integration over k prime, and the integrand is 1 over k minus k prime squared. So it is a logarithmic function of k minus kf. So let me just show you the result. 2 plus kf squared minus k squared divided by k times kf times logarithm of this k plus kf, k minus kf. So I assigned this to you as a homework exercise to derive it. Okay, so the answers are everywhere in the reference books, in Kittel's, Ashker, Merman, everywhere, that you simply just integrate this three-dimensional integral over dk prime and of this 1 over k minus k prime square. When you finish this, and you get this logarithm. So you see, just by looking at this, the log behavior of this exchange energy term, that you immediately notice that this must be very singular when k is very close to kf, because this is 1 over log of 1 over 0, right? So this log something k plus kf divided by k minus kf. So when k is very close to kf, this is log of 2kf and 0, right? Okay, so when k is very close to kf, you get a very, very singular logarithmic divergent term from this. And therefore, you immediately see that this consequence of the Hatree-Fock treatment is the singular behavior of a quasi-particle energy near this Fermi surface. Very singular. So let me finish and reorganize everything. So this is given by h bar squared k squared over 2m e squared kf over 2 pi times f function k over kf. So this f function is just this complicated, messy log term over there. If you plot this f function, x is defined as k over kf, and this f of x, and this is 4, and this is 2. Okay, so the f function has this continuous jump right at the Fermi momentum when x is equal to 1, k equals to kf. So f of x goes like this smooth curve decreasing from 4 to 2 right at the Fermi surface when x is equal to 1. This value of f of x just jumps to 0 right away. As a result, the dispersion of the quasi-particle excitation energy for electron experiences a sudden jump in the dispersion right at the Fermi momentum. And such a jump indicates that the density of states right at the Fermi surface of such a quasi-particle is actually almost 0, because we could very easily calculate the density of states at the Fermi surface of such electrons within the Hatree-Fock, and you will see that the density of states at Fermi surface is actually 0 because of this sudden jump of this f function due to the log dependence of this exchange energy, k minus kf. So let's just calculate the density of states. Remember, in solid state 1, you are familiar with density of states, which is inversely proportional to the slope of your dispersion, right? So, for example, this is the electron dispersion, this free electron gas, where you have this quadratic band, right? And so the density of states near this Fermi surface is actually inversely proportional to the slope of this dispersion at kf, right? So for a quadratic band, it is inversely proportional to kf, right? With some proper prefactor, because epsilon is proportional to k squared. If you take the derivative k squared, you get k, and k is very close to kf. You get 1 over kf, which is constant for ordinary metals. And this is what we expect, that this density of states is the number of electron states per energy. So the number of electron states for a quadratic band is actually a constant, very close to kf. And this quantity is actually a constant. So this could be confirmed by experiments. If you measure this kind of a tunneling conductance of normal metals close to 0 temperature and this Fermi level, you'll see this constant conductance peak, right, near the 0 bias. But within the Hatree-Fock, this is almost 0 because you'll see that this jump over here. So apart from this quadratic band, you get additional term which depends on this f function, but the f function experiences a sudden jump, right at the Fermi momentum. So if you evaluate this slope or derivative, first derivative of this quasi-particle band within the Hatree-Fock, you'll get some constant which comes from this quadratic band, plus or minus something very, very singular. Because if this is just a vertical jump, and you take the derivative of this f with respect to x, you get infinity or minus infinity, right? So this plus or minus infinity, if you take partial f partial x, s equals to 1, right? Because this is a sudden jump. And whether this is plus or minus infinity doesn't matter. You simply add the infinity in the denominator in addition to this constant density states, and therefore you always get zero density states, which is totally wrong, because we expect that this electron density states for ordinary metals near the Fermi surface is a constant. But the Hatree-Fock theory predicts that the density of states near the Fermi surface is actually zero, meaning there's no electron, almost no electron states populated near the Fermi surface within Hatree-Fock, which is totally wrong. And you know why this is wrong? Of course, this is due to the long-range nature of the Coulomb potential treated by the Hatree-Fock. Okay, so let's call it a day, and we continue on Wednesday for other predictions, and we will start a new chapter which allows us to rewrite this Hamiltonian in a totally different language, namely the electron density operator. Okay, so please read the corresponding chapters in David Pine's lecture notes, and also Flansburgh and Kittel's on this part, and we will Coulomb screen this screen the Coulomb potential probably a week from now. So I'll see you on Wednesday.